All right, good afternoon, good morning, good afternoon, good evening. Welcome to our webinar on the trace ppm level process oxygen measurement and when to consider optical quench luminescence to be presented. Joining me today for the session are your regional contacts, Stefan Gui, Business Development Europe, Sean Matthews, Business Development in India, Justin Tucker, Sales Engineer Middle East. We intend for the session to be educational and informative on process oxygen measurement with a broad overview or refresher on available technologies before diving into the quench luminescence and a few applications. Okay. Before we dive in, we would like to cover a few logistical items. So if everybody can go ahead and please put your teams on mute. So of course, if you're not familiar with it, this is the mute button right here. There we go, back on there. Also, if you guys have any questions, we're going to try to, so we are recording the session, also let everybody know that. Second thing is if you do have any questions, please go ahead and log those into the chat as they come up. And then I'll try and take a break about halfway through. We're going to go about 40 minutes, but we'll want to leave some time for questions here at the end. So your chat dialogue is right here, and go ahead and you can put in any questions that you may have. Okay. So the overview of the presentation today, we'll do a quick company introduction, and then we'll talk about why is oxygen important to measure, review of common measurement techniques, pros and cons of Zirconia, TDL, Paramagnetic, and E-Chem. Then we'll dive into the quench luminescent techniques to measure oxygen. We'll talk about the theory of the implementation and then a little bit about performance specs, do a quick overview of some of the hardware and how to get the analyzer and sensor into the process, and then talk about a few applications from there. So a quick overview of the business unit. This presentation or webinar is sponsored by our business unit, AMETEK Thermal Process Management. We are part of AMETEK, Global Manufacturer Electronic Instruments, Electromechanical Devices. This AMETEK Thermal Management business unit is comprised of 5 different companies. It's comprised of CSI, who provides trusted thermal process solutions to plants around the world, tracing and heating solutions, sulfur process solutions, and winterization. O'Brien supplies tubing bundles, enclosures, instrument stands, and solution services, known under the brands TracePak, HeatPak, and BiPak. Cardinal supplies to the semiconductor industry precision electropolishing and specialty clean piping components. Universal Analyzers produces gas sample extraction, transport, and conditioning systems for SIM and process measurement. Barben Analytical manufactures analytical pH, ORP, and conductivity sensors along with optical quench luminescence process oxygen analyzers. So why is oxygen important? So many of us are familiar that there is a good amount of oxygen in the atmosphere, 20.95% or otherwise 21%. But not everyone knows that oxygen is also the most abundant element on Earth, comprising 47% of its composition. And it is the 3rd most abundant in the universe, little misleading because the Milky Way has 74% hydrogen and 24% helium, and just 1% of oxygen in the universe composition is just a little bit underneath the 1%, but still the 3rd most abundant element in the universe. Here on Earth at standard ambient temperatures and pressures, 2 atoms combine to make dioxygen. So that's the way we'll commonly find it. It'll be the 2 atoms come together to make O2. It is a very highly reactive non-metal and an oxidizing agent that readily forms oxides. So it is very critical to many biological processes, including breathing. That's how we get a lot of our energy, or that's how we get our energy. is through the combustion process of breathing, respiration. And then it also touches us every day in our modern life in power, fuel, and heating. It's also very important for industrial processes in combustion, oxidation reactions, corrosions, quality, and safety. So why is it important for us to measure, and why do we say it's important in those industrial processes? So for combustion processes, O2 is measured to ensure excess stoichiometric amounts to promote efficient combustion. Okay, however, too much will reduce efficiency by lower temp and throughput. So if we take a quick look here at this graph, we can see is that as you add it, right here is the stoichiometric amount, okay, which means that we have just the right amount of oxygen to combust with our hydrocarbon to give us a combustion product. We have just the equal amount of moles, and that is here. But what we need to make the reaction the most efficient was we need excess oxygen. And so that actually happens over in this area. But if we continue to add oxygen, there's some point at which our efficiency will start to drop off because now we're adding so much air or oxygen or air in the oxygen in the form of air that we'll have lost heat going up the stack. Okay, so oxygen is a critical measurement in all the combustion processes. Okay, and so that means that it's going to be very important since combustion processes are very enormous throughout the industrial processes and power industries. That's a huge amount of energy and also a very big environmental parameter for people to measure for efficiency. And then the second most common reason would be safety. So in this case, we want to prevent the combustion itself and prevent combustion or in the form of an explosion. O2 is monitored to ensure oxygen stays below the lower explosive limits. So really quick, I'm sure most people are very familiar here with this triangle. And the idea here is that if you have a process that has a fuel or a flammable substance, that we just want to operate with just that, and we want to make sure that we never get enough oxygen to be sitting around and waiting for the ignition source. Because if we live with two and we wait for one, then we're going to find at some point the explosion. So we only live with one of these legs of the triangle. It's also very important for process efficiencies and product quality, okay, such as unit operations. For example, an amine unit, amines are used to scrub or sweeten H2S and CO2 removal from LPGs or natural gases or those types of products. And if oxygen gets in there, it can go ahead and eat the amines and lower the efficiency of the process. Also, you have we want to remove oxygen or make sure that it doesn't exist in a process to slow the oxidation or allow for reducing reactions to occur. This is our case with food, annealing furnaces, also to protect catalyst, or in a fiber optic coating operations. Also, the fourth biggest thing is to protect against corrosion. So dissolved oxygen, so oxygen in the form dissolved into liquids, and then gas. In the gas form, oxygen can be very corrosive. So this is very commonly measured in the steam generation to protect boiler and condenser tubes and turbine blades. Oil and gas industry, enhanced oil recovery, water flood, and produced water. So this is a very interesting thing that most people aren't familiar with, I find, is that we're very worried with our NACE standards about H2S. But if we look at this chart here, I know it's pretty hard to see here, but I'll just read it off a little bit. It shows that H2S okay, excuse me, oxygen is 80 times more corrosive than CO2 and 400 times more corrosive than H2S in water flood and produced water applications. So this is saltwater stuff inside of downhole tubes, produced water, and water flood piping. So trace O2 is also present in as acid gas, excuse me, trace O2 in the presence of acid gas, H2S, CO2, or H2O, oil and gas production, gathering lines, gas plants, biogas, anaerobic digesters, sweeteners, sweetening, storage, and transmission lines in a biogas process. So how do we measure these things? So we know now that it's very important to make this measurement. So there are several different devices out there to do that. So we kind of put this page together just to give a quick review of what's out there, what you may choose to go ahead to make that measurement. So combustion analyzers for zirconia and for flue gas applications, high temp sampling. And I put down a few of the different general price ranges of the devices. All the way some of these to a pretty extreme number depending on the sampling system or maybe the seals that are involved in that. But here's just kind of a general landscape of the analyzers that are out there. I didn't, and then we're going to go through these top ones. I didn't add some of these because the mass spec and the GC are not devices that you get just to measure oxygen on its own. They can be used to measure oxygen, but generally people aren't going to go get a GC to measure oxygen. They'll have a GC for other reasons and then measure oxygen, but not a single point by itself. So zirconia oxygen cells. So what we know here is that ionized O2 passes through zirconia oxide around a temperature of 650 degrees Celsius. The O2 can ionize and then it can go ahead and pass through what is a solid substrate, but very porous, like a ceramic material, zirconia oxide. Okay, and so what happens here is we have a sample gas inside. It'll have a partial pressure of oxygen, PO2, of our sample, and then it'll be in contact with this platinum electrode, and then you'll have a ambient air reference here under its partial pressure with a 20.9% concentration, and that differential will drive the O2 through the platinum, and we will then get a voltage that will develop between that's relative to the difference in concentrations, and we'll be able to measure that with a voltmeter. The pros and cons considerations is that it's extremely reliable at high temps and ambient pressures. Simple system, okay, whether it be an in situ application where we put the probe directly into the process, or a hot wet extractive where we're pulling it out, but we don't have to do any sample conditioning because we can keep everything hot. We don't get anything condensing, run it by the zirconia and make the measurement. So super big pro on this simple system for in situ and hot wet extractive. The downsides of this technology is it can be poisoned by sulfides and halogens. However, that only occurs at reducing conditions less than 1% O2. And generally, most applications are combustion and oxidizing. So we're going to keep those at a higher 3% or higher level that'll be and won't be damaged by the sulfides or the halogens. It is also biased on combustibles, can cause low O2 readings. If we have any combustibles or CO, that can go ahead and hit the platinum at the high temperature, it will react all the way to CO2 and it'll take an oxygen from our sample gas. Same thing if there's any unburnt CH4 from inefficient burners, is that can also combust at the platinum here and then steal some O2 right at our measurement point. And that would then cause a low O2 reading. The good news here about this is that combustibles and CH4 methane sensors can be added. Companies like Thermox provide units like that on their closed coupled extractive units. If you want, but that would be something to be aware of if you're looking at an in situ unit, that it could have some low readings with uncombusted products. The cell is heated, so another con is that the cell is heated to 650 degrees Celsius. And that means that it cannot be used or should not be used for flammable process applications. The applications that it's good for is combustion, flue gas applications, and inert gas applications. Really quick here, overview of tunable diode lasers. These can be pretty complex devices, but really we kind of looked at one here that near infrared laser, finely tuned for the analyte, and these can very uniquely detect the specific analyte of interest down to a very trace level, passes through the sample to a photo detector. So this is the gas inlet coming through the sample cell. You can see the laser comes in, hits a mirror, comes down, reflects back, and then comes back and hits to the detector. Okay. Some of the top-end TDLs use wavelength modulation spectroscopy, which really helps in the absorption ability to achieve more finite results. And then you'll find that some of the lower end TDLs can have a lot of interferences. However, the newer and higher end TDLs use chemiometrics, which is basically modeling that will effectively remove the impacts of interfering species. Okay, so the pros and cons here of a TDL are reliable non-contact hot, wet sample. So it's okay if the lens gets dirty because they don't need much of a signal strength to be able to see the absorption that is occurring from the analyte. The one thing you have to do is make sure that you keep the sample system must prevent condensables. We don't want any condensables on the windows. Other than that, but you can keep a pretty high temperature, so that's not too hard to do. No calibrations required. That is a fantastic thing about the TDL, that you can use a reference cell and a laser lock, achieve a laser lock on a reference cell, basically a calibrated gas of your specific analyte that you're looking at. Has a fast response. And can measure other gases. So the same device, you can have dual cells and you can measure another analyte at the same time, or you use the same analyzer for different gases such as H2O, H2S, CO2, or other light molecules. Accuracy for O2 is less than 1,000 ppm become challenging. So that's the con about the devices. As we get to 1,000, then measuring below 1,000 ppm for oxygen becomes a challenge for the device, especially not going to happen anything below 100 ppm, which a lot of the applications for the quench luminescence will be. Okay. Applications for the TDL, O2 and CO and combustion monitoring, hydrocarbon process tank headspace, vapor recovery flares, and many other process applications. So let's say thermoparamags. So I kind of group these together. There's several different techniques. I pulled a couple here. I think that they do rely upon the same main principle. They use the paramagnetic property of oxygen to create a differential in flow across some physical device. And whether that physical device be dumbbells, which are going to twist, and this is where you have two balls here, dumbbells that are filled with an inert gas, and as the oxygen goes by, or the sample goes by, and the magnetic poles will influence the direction of that, it will deflect this to a proportional amount, and then it's measured by an optical system there. But the same thing as if you do it with a thermal resistor, or if you do it with the measuring devices, pressure transducers, which helps to protect some of the stuff, but still can be sensitive to moistures and particulates getting into the system. The pros are sensitive over large ranges and can measure in many processes. The cons are sample systems must prevent condensables or the cell will fail, and the temperatures are lower than some of the TDLs. It also does not like high particulates. It does have interference from background gases, and these must be considered. You either have to do it, take them out via the calibration gases, or to do the calculated amounts and looking for a steady state process of some of those constituents. And then the lowest limit of detection for most of these devices is 100 ppm. It really starts to struggle, and most of them start to struggle somewhere around 1,000 ppm. So again, for a lot of the critical applications, that's where you're starting to get a theme of where this quench luminescent may belong, is in some of this trace level applications. Applications where we find these O2 and CO in combustion monitoring, hydrocarbon process, tank headspace, and many other process applications. So the guy who has filled the space of the trace level oxygen measurement for the industry has really been the E-Chem cells, the galvanic and the Clark cells, kind of group those again together. And for good reason. There are some differences between those two technologies of E-Chems. However, they are all still based on an anode and cathode system with an electrolyte, and then also they depend upon a gas permeable membrane and then a reaction to produce a signal current. So as you see here, this is the membrane right here, and that is going to be a source of some pretty big pain for this device. And then, so what happens here on this sensor is that you have your process O2, and the process O2, this is a gas permeable membrane. So it's going to go into the electrolyte, transfer in there, and we'll go ahead and start to get a reaction, and then we'll have a current loop through the process with these electrons. However, with that being said, this thing we can say is good because it can do both gas phase and liquid phase dissolved oxygen. Good for trace and percent level O2 and process streams. You just have to change some of the sensors to get the difference between a trace and an O2, but the analyzers stay the same. As long as they don't have any H2S or CO2, because the H2S will go ahead and directly attack the silver anode by making a silver sulfate as a precipitant. And then the CO2 will start to poison the electrolyte, making the caustic electrolyte down to a acidic electrolyte. Highly problematic membrane fouling. So this whole reaction and the measurement of oxygen and the determination of oxygen is dependent upon this reaction and the mass transfer of oxygen across that membrane. So if the membrane gets fouled, then less oxygen is going to go in there, and we are going to read low. As the membrane gets attacked by chemicals, it can break down and it won't be as gas permeable, and the reaction will be slower and the reading will go low. The membrane is also susceptible to pressure and temperature changes that can affect the mass transfer. And then we have the poisoning of the electrolytes and the electrodes. And so really the accuracy becomes pretty suspect, especially since everything is drifting to a low direction. So what that gives us is the worst part about this thing is that it fails low and it drifts low. So in most of the applications where we're talking about corrosion, where we'll see a lot of this trace stuff, or product efficiency and product quality, most of the time folks are looking for zero oxygen in their system. And so if your measuring device tends to fail and drift low, then it will give you a false sense of security that everything's okay and you don't see what your problem is until you have bad product or you have corroded pipe works, which could be some major assets worth tens of millions of dollars. So that's what's going on here with this galvanic and Clark cell. The applications that it is used in and good for. So it is good for transmission natural gas lines. I say transmission because that's where we've already cleaned up the natural gas, removed the H2S, CO2, and the moisture. And they work very well in those applications. They work very well in clean semiconductor applications. They're the only ones who can do to the sub ppm level, to parts per billion in the gas phase. They do very well at inert gas applications and dissolved oxygen. All right, so with that being said, I'll take a quick look at questions. Go ahead, please, if folks got any on what we just covered, let me know there. I'm going to move into the quench luminescence technology. So only going to jump into it in so much detail, but definitely open to any questions as we have to understand more. So quench luminescence technology, we flash an LED. The LED comes down a fiber optic. So this portion here is contained within a sensor, okay, and sealed from the process. This part here in the front is exposed to the process. And so this LED flashes, comes down, and it hits this luminophore. This luminophore becomes excited. The molecules absorb that energy. They become excited, and then naturally, they will go ahead and relax back down to their ground state and let back off that energy, and that'll go back in the form of a red-shifted photon. And we look at that as these red arrows going back, and we'll detect how much light comes back to our device, and that will be proportional. So that's the case with no oxygen. And then in the case with oxygen, what happens is we flash the blue light, it comes down, it excites the material, and then when the material is excited, the oxygen can collide with that material. It will quench that energy, and then less light as a population, when we look at it as a population, less light will come back to our device. And we'll see that as directly related to the concentration of oxygen. Okay? Same thing as we just saw on the other page, just doing it in a little different molecular diagram, but the same principle we just talked about, the blue light coming down, absorbing onto the molecule, it getting to an excited state, and then after it's naturally, without any oxygen present, it'll emit that energy in the form of light, and that'll go back to our device. Now, with the oxygen present in the system, what happens? The blue light comes in, the molecule absorbs that light, goes to an excited state, and then when it's in that excited state, with the presence of oxygen, can collide, and it'll steal that energy, and we'll have no light come back from that molecule. As a population with a few collisions of oxygen, we'll see that as less light coming back. Okay, and so that's what this graph shows us here. So what we do is, so we look at here and say at the 0% oxygen, this graph over here to the right, at time 0, we can see that we have a relative intensity of 100% or 1. And so, and we see that as it starts there at time 0, and then we have a certain decay rate over a certain amount of time. Whereas in the presence of 100 parts per million of oxygen, at time 0, we now immediately start at 0.9, and that is because some of that light from the population has been quenched from the presence of this oxygen. So immediately we have less light coming back, and it decays at a faster rate. Okay, so that becomes important for us because we could, and people did make the measurement off of this difference, the absorbance difference, for many years. But the problem is putting that into the field becomes problematic because we would have to know exactly the output from the LED, and then also the fiber optic cable. If it moves, the light intensity could shift as we lost a little bit of its efficiency in the fiber optic. There would be lots of different perturbations that could affect this differential. It's still a pretty decent measurement. We use this as a diagnostic, but to get rid of some of those perturbations and to make this a very accurate and reliable measurement under field conditions, we look at the time difference here in decay, and then we move that into the time domain by using sinusoidal modulation of the excited LED. And then we're able to measure this in the phase angles. Okay, so what we do is we just flash the light and it is modulated here as the blue. And then we go ahead and then we can see, we use a reference light, we flash it, and then we look at our measurement come back, and we just look at the difference between those points, and we're able to calculate the phase angle or the decay time between the two, which is directly related again to the oxygen concentration. So that's pretty much the tech that is behind this quench luminescence. And what does that look like to us? So here's a BOS3 trace gas range sensor. This is the phase angles over an entire range of 1,000. So we published this range, this sensor, from a 0 to 300 range. Right here, you can see that there is a lot of resolution of phase angle per oxygen concentration. And so this whole range from 0 to 300 was within our published accuracy spec. We do go ahead and allow to measure after this, and this is what we call the over range. Okay, is this range right here, but you see that it's a lot flatter, so we have less resolution, and we can track very good. So a lot of customers do like to still look at that range, but it is a little bit outside of our published accuracy spec, which is that 0 to 300 range. And it makes sense for a lot of folks that are trying to measure zero again, or trying to measure a 0 to 10 parts per million system, that they want to look here, but then when they have a leak in the system, they want to see how high it goes, because they may be looking at a very large volume of gas. So the difference between 5 ppm and 200 ppm is a massive amount of air coming in from somewhere. If you're looking at a large gathering line or a gas plant or something of that nature. Okay. A BOS1 mid-range sensor. This shows the response here of our published range on this guy is 0 to 4.2%, and we do an overrange to 5%. Again, pretty good resolution over the published range of accuracy, and then decent follow from the 4.2 to 5. Then if you look here at the low end of the sensor, you can also see that it has a very good accuracy. This thing goes all the way with a low limit of detection down to 20 ppm, and it has a rangeability up to that 0 to 4.2%. So that is quite a big turn down ratio, I guess we would call that, to be able to measure so big and so low also. Not shown. I didn't pull the graphs for the BOS2, and that goes from 0 to 100% O2 with a low limit of detection of 300 ppm. I did want to show the BOS1 though. Same sensors we showed in the gas phase can measure in the liquid phase. And it can measure the dissolved oxygen over the range of 0 to 1800 ppm. And then also a low limited detection of 1 parts per billion. And you can see here is that we have a range here of 0 to 50 parts per billion. So this would be something that would be used in the floodwaters or the produced water applications. A lot of times our customers are very interested about operating right here at the 0 to 10, 0 to 20 parts per billion. And we're able to do that with this BOS1 sensor. Not going to go through all these charts right now. Just wanted to bring these up to say is there is one thing about the technology that we have to understand, and that is that this would be a con to the tech is that it does have a drift rate that is dependent upon the sample rate. So it's not much. So the good news about that is that it's not a lot. And if we don't measure at a very fast rate, we don't need a very fast sample rate. And then also that it is very repeatable and linear. So for instance, here at a very normal, a lot of the times our customers use sample rates of once every 60 seconds. And you can see is that over a time of 28 days or nearly a month, that we can say that we would have less than 1.5 parts per million of drift in the upward direction. Okay, it's always in the upward direction. All of our drift and all of our failures are in the upward directions. So we'd have 60-second sample rate, less than 1.5 ppm of drift over 28 days. So that's what this guy says. Calibration is done as nitrogen-based zero and span gas. We don't worry about interferences from background gases. Even though it's an optical technique, it is optically isolated from the process. And therefore, we don't see a luminescence from different materials that are in there or worry about those types of things. It is optically isolated. We're just looking at the oxygen that's in the system, very specific to oxygen. One thing that we do need to know though is this is a partial pressure. All of the different devices that we looked at today, whether it be the TDL, the Zirconia, the E-Chem, and the Paramag, they're all partial pressure of oxygen devices. So while we're talking about oxygen, it's good to understand a little bit about partial pressure. So partial pressure is really just the concentration times the pressure of the system at that point. So it's really just a multiplication of those two numbers is the partial pressure. So give you an example real quick to try and bring that to light. What that means is that a lot of folks think that if I climbed Mount Everest, that we'd have issues breathing because of the lack of oxygen concentration. But that's not the case at all, because actually oxygen is 20.95 all the way from sea level all the way up to the top of Mount Everest. The concentration doesn't change. But what does change is that down at sea level, here's a case of London, is published at 754 millimeters of mercury at sea level. And at the summit of Everest is 253. And so since the concentration is the same, that means that the partial pressure of oxygen is 148 in London, and it is only 43 millimeters of mercury at the summit. So that is a lot less up there. And that is what the people, because your lungs work on a partial pressure of oxygen, your respiration system. And so without the partial pressure, you just cannot breathe properly unless you acclimate properly. So it's all about the partial pressure. Just a little bit more about partial pressure is that you know the sum is of the total pressure is equal to the individual pressures of each component in the system. So if this was air, for instance, so we'd say this was 1 atmosphere, okay, if we were saying at sea level. And then this would mean is that the nitrogen would then be 0.79 and the oxygen would be 0.21 atmospheres, partial pressure of oxygen, okay? Once we know the partial pressure, that's what we measure, and we do this by the ideal gas law. But just cutting to the chase here is that since our device measures the partial pressure of oxygen, as long as we know the pressure of the system, we can calculate the concentration. It's really that simple. But the point of the matter is that we need to know we're measuring this. We got to know the pressure of the system when we measure and when we calibrate, okay? If we're using a sample conditioning system, then that's great. We can do the same pressure all the time. We don't need to calculate it or measure it. But if we don't, and we're going to put our device inside of a process pipe or something of that nature, then we will need to put a pressure transmitter on there and compensate for the differences in pressure that may occur. Or if we're going to calibrate at a different pressure than we measure, we need a pressure compensation device. Good news is that the analyzer supports that. So now now that we know a little bit more about the pros and cons, we'll kind of wrap that up of the quench luminescence in the same way we looked at the other technologies and say is that optical quench luminescence that uses an LED to excite a luminophore at a specific wavelength and observe the phase shift in the time domain. The pros and the con considerations are trace ppm. The pros are it's a trace ppm range to percent level measurement with a very fast response. Trace to ppm dissolve the oxygen in liquid with same analyzer. And then it can also do the sensor remote from electronics and capable of ambient conditions. So that means that you can take the sensor and move it away from the electronics and put it into the process in some cases, or we can have it in different areas if necessary. We can do both in situ and extractive. And we do have to watch where we do the in situ because we are limited here by things such as temperature. Okay, so as long as it can only go in process if the temperature of the process is below that 50 degrees Celsius. The con here is also it can be harmed by organic solvents and strong oxidizers. So this has to do with the element that's into the process. So we do need to get a chemical composition and understand that if we start having percent levels of benzene, toluene, xylenes, THFs, hexenes, butenes, chlorines, a few other different things such as some acrylates, then we need to look at that and make sure we avoid those. Now they don't cause incorrect readings, but they can cause shortened life and more drift than we were publishing there before. So those are the things that we need to avoid. But when we don't have those things, the thing works extremely well for trace level measurements, and it can do very well with regards to replacing some of the E-Chem that is in applications that have some of the poisons, such as the H2S and the CO2. So this does very well. The applications we'd say where this guy shines as hydrocarbons with H2S and CO2. You find that in biogas and renewable natural gas applications, both in the production, in the cleaning, scrubbing, the transmission, storage, those types of operations. And also in hydrocarbon gathering, sweetening, and production upstream market and midstream marketplaces, sweetening and vapor recovery units, EOR water floods, and and dissolved oxygen, and then also pure ethylene and propylene applications. I'll go through some of this real quick because I want to get to, I'm running short on time here as far as the target of 45 minutes. So I'm going to just go through, this is just a couple arrangements, and then we'll talk about some of the applications real quick. The general arrangement of the device, this is a flow cell pressure transmitter right here at the top, the RTD for compensation of temperature, and then the oxygen sensor itself. Okay. Just showing you a couple pictures of it. Here is the replaceable sensor cap. All the rest of the stuff is meant to last the lifetime of the installation. It is just a replaceable sensor cap. It takes a few minutes, and those go anywhere from 500 to 600 US dollars in that neighborhood. The general installation of an extractive unit. This is for a wet gas sampling, has a fast loop, so it has a little bit of extra stuff on here, but that's a general arrangement. Want to say is that the same sample panel as before, except for now this one has some solenoids to do an auto calibration. So quench luminescence can be supported. This device here is supported to do a auto calibration routine and can be set up in the field to do so. This common example shows that this stuff is also field suitable in most environments. With a rain and a sun shade, this stuff can go out in the field. Here's that sample panel, and here is the auto calibration solenoid panel, and then the analyzer itself. Okay, outfield mountable. The next thing too is the in situ arrangement. Okay, as we can see here, class 1 div 2 or zone 2 installations. We can also do zone 1 installations this way. We show here is the analyzer in a liquid process, maybe produced water or a floodwater application, going directly into the process. We don't need, water is not compressible, so we don't need pressure compensation there. And then here we're showing one in a gas pipe in situ where we do have our pressure sensor here also attached. The RTD is actually integral and goes into the tip with the oxygen sensor. This type of device can have all the proper ATEX IEC zone 1 and zone 2. Has a pretty good list of applications in the upstream, midstream, downstream. Some manufacturing. Last few things here, water flood application. So a water flood application is used to keep the pressure on an injected downhole. So what this means is an offshore rig, you're pulling oil out, and as you pull the oil out and displace it, the pressure can lower in the reservoir. So to be able to overcome that, you grab some seawater and run it through some cleaning processes and downhole. This is a very high pressure application. As we said before, is that oxygen can be extremely corrosive to metal in high pressures, and so this is that case. We need to move the oxygen before we put it down whole. And so that's what this application is about, the simple filtration, and then we have some deaeration, either from a nitrogen or through a standard deaerator with steam, and remove it, and then some oxygen scavengers, and then a sulfate removal unit, because we need to, after we remove the oxygen, sulfate can be converted to an H2S, which would sour your oil reservoir, and we don't want to do that. So they inject it down hole, and there you go. We want to monitor the different points of that process with our PPB trace quench luminescence device. Okay. People typically used existing technique was electrochemical, which it fouls and plugs, it becomes very unreliable, and it drifts to zero. And then the operators understand that it's drifting to zero, and then they will start to overdose the chemicals. And when they overdose the chemicals, two things go bad. Number one, it is a large amount of seawater. And so any parts per million chemical addition is a very large volume of chemicals. And then the second thing is that as they put more chemicals in there, they adjust the chemistry from what the chemist said was perfect or the best chemistry zone for them to do. So um, a Mirox application, this is simply a mercaptan extractant process to remove some of the mercaptants with a caustic stream. So we have the separator here in that process. And what happens, we need to separate the caustic from the disulphide in recovery. And there is a vent that comes off of there. And this is a very common place for us to measure oxygen. Amine sweetening plants, I did mention this earlier, is that the amines are used to sweeten a lot of natural gas streams or LPGs to remove the CO2 and H2S. O2 is a very big contributor to lowering the efficiency of the amines, and so we want to make sure that there's no oxygen in that system. Okay. This one has been pretty big for us, along with that floodwater and EOR. The floodwaters and EORs are located all over the world in the North Sea and over in the Middle East and also in the Gulf of Mexico and some in Asian waters too, and then off the coast of Africa. Wherever they have deep water stuff, that they'll use some of that floodwater technique. And then the renewable biogas is pretty big here in the States and then also over in Europe. And we're finding some key applications to where that in situ probe coming off that wet anaerobic digester with that wet H2S, CO2, and natural gas, putting that directly in line there has worked pretty well. And then we have around the scrubber system here, and then also on the RNG, the upgraded natural gas before it goes to the transmission lines or to storage. Again, if you use an electrochem for those applications, that H2S that's present in there will fail those things low, especially with the moisture, the H2S, the CO2. They're going to be very problematic in these types of applications. And then if you try to use some of the different technologies, you can't use the zirconia because of flammability. You can't use you can come in with the paramag, but if you had the saturated stream to take off as soon as you get moisture, that's very problematic. Been very successful there at that point. So thank you for attending today's webinar. We hope you found it informative. It was a good review or even new information for some. Even more so, we hoped it provoked further interest in the different available technologies and the use of quench luminescence in key process applications. The quench luminescent technology provides the process industry solution for trace to percent level oxygen measurement in hazardous and non-hazardous process applications, especially as a solution in place of others for trace ppm with contaminants such as high particulates, liquid breakthroughs, H2S, CO2, and moistures. So any questions at this time?
Yeah, well done, Melvin. It was very informative, even for me. So I do believe many people appreciated this. There has not been any question in the chat box. If anyone has a question, feel free to speak up or write it down, however you feel like.
Yes, and also if you feel like on email, we're open for any of the questions. No, we do not have any SIL. So we had a question come through is saying, is this available with a SIL certificate? And the answer, unfortunately, is no SIL rating on the safety integrity level. It does not have one. Sorry, but thank you. Good question. because that has come up several times for the technology. Changing the sensor. So we have a new question here. It says changing the sensor needs any special configuration on the electronics. And so the answer is no for our standard sensors, and that covers 99% of what we do, meaning that it doesn't take a configuration or anything like that. You basically take off the old cap, you put on the new cap. You can punch in the factory values and be very close, but we do recommend you would do a calibration in 0 and span, and you'd be ready to go.
Okay, Melvin, maybe we should wrap this up now.
Yes, I really appreciate it. Thank you.
And thank you, Melvin.
All right, thank you guys.